Like a waterfall in slow motion.
Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course. So now we're just going to wrap up with a series of a couple practice problems to see if we can apply the concepts that we learned in this video to some actual questions. So the first question is, between these two compounds, which has the higher boiling point and which is more soluble in water? So the one on the left is propionic acid and the one on the right is methyl acetate. Well, boiling point can be viewed as a measure of how strongly the molecules associate in the liquid phase. Stronger associations require more energy to break. Therefore, molecules with stronger associative forces have higher boiling points. Molecular association can occur in order of decreasing importance with anion-cation attractions, dipole interactions, and London forces. Now, neither propionic acid and methyl acetate are ionic, and so there are no ionic attractions to consider. Both have a number of polar bonds, and so these are CO and OH bonds. So both of these are going to have considerable dipole-dipole attractions. Now, the propionic acid molecules can associate with other propionic acid molecules by donating and accepting hydrogen bonds due to this carboxylic acid group. On the other hand, there are no hydrogen bonding possibilities in pure methyl acetate. So propionic acid has more attractive forces between molecules than methyl acetate. So therefore we can predict that the propionic acid is going to have a higher boiling point. Now for the second part, which is more soluble, the solubility can be viewed again as the strong association of the solute, and so this is propionic acid or methyl acetate, with the solvent, and so in this case it's water. So propionic acid can both accept and give hydrogen bonds with water. Methyl acetate can only accept hydrogen bonds from water. And so therefore, because of this, we can predict that the propionic acid is going to be more strongly associated with water and therefore more soluble. So in this case, the propionic acid is the right answer to both of these questions. Question number 2. Is squaric acid soluble in water? So this is the structure of this compound. And again, remember that solubility occurs when the number and or magnitude of attractive solute-solvent interactions is large. So squaric acid is both a hydrogen bond donor and acceptor. So these carbonyl groups, the oxygens here on the left-hand side, are the hydrogen bond acceptors. The hydrogens attached to the hydroxyl groups on the right-hand side are the hydrogen bond donors. And so because of this, it can form many attractive interactions with water. Many dipole-dipole attractions are also possible as well. So all portions of squaric acid are attracted to water, and so therefore we can predict that it does have very high solubility in aqueous solutions. Question number 3. Explain how noncovalent molecular forces can influence or affect the boiling point of ammonia. So let's draw that out first. So let's consider all of them one at a time. What about anion-cation? Well, ammonia is not ionic, and so there are no anion-cation attractive forces to consider. As for dipole-dipole, these interactions result from the electrostatic attraction of polar bonds. So atoms bearing a partial positive charge are attracted to atoms bearing the partial negative charge, or an electron source such as lone pairs. Nitrogen is more electronegative than hydrogen, and so the nitrogen bears a partial negative charge and the hydrogen's partial positive charges. So there are 3 polar bonds in this molecule, and this also contributes, or this results in an increase in the boiling point of ammonia. Next, we consider hydrogen bonding. So this is basically a dipole-dipole interaction for cases that involve a hydrogen atom. So in this case, again, this increases the boiling point just like the regular dipole-dipole interactions. And then finally, London forces. Well, so as two molecules approach each other, their electron clouds repel. This results in an area of low electron density, partial positive charge on one molecule. The other molecule's electron cloud is attracted to this region and distorts itself towards the partial positive region as a result. So again, this creates an area of higher electron density, partial negative region on this molecule. And then the partial positive and partial negative areas are of opposite charges and therefore attract each other. These electron cloud distortions are very brief and very weak. And they result in very small molecular attractions, but they're possessed basically by all molecules. Now we can note that these polarizations may also occur just due to random fluctuations in the electron cloud densities. But in the case here for this question, London forces, of course, are present. So this can also contribute to the boiling point of ammonia, but to a much, much lower extent than the typical dipole-dipole and hydrogen bonding interactions between ammonia. So this boiling point is rather low if you consider it or compare it to, for example, water that has 100 degrees Celsius. But in any case, attractive intermolecular forces result in higher boiling points than if those attractive forces were not present at all. Finally, we'll do one more practice problem. Rank these three compounds with order of increasing boiling point. So we have ethanol on the right-hand side, propane, and then methyl ether. So we'll consider the intermolecular attractive forces in each case. So the strongest of these is going to be the anion-cation attractions, then dipole forces. The weakest are the London forces, which are possessed by all of the molecules. So remember, stronger intermolecular forces result in higher boiling points. Propane in the middle has only London forces, and so it's going to have the lowest boiling point. Methyl ether on the right-hand side has London forces and dipole-dipole forces due to the polar carbon-oxygen bonds. Therefore, the methyl ether is going to have a higher boiling point than propane. Ethanol has London forces, dipole-dipole attractions, again due to carbon-oxygen bonds, as well as hydrogen bonding. Therefore, the alcohol, ethanol here, is going to have a higher boiling point than methyl ether. Therefore, we predict that the propane is going to have the lowest boiling point, then the ether, and then the alcohol.